and welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but still want to be its friend.
I'm Connie, your curious co-host.
And I'm Dr. Moiya McTier, your other co-host. I'm curious, but I also am here to, sate your curiosity with the things that I already know.
Yeah, you are curious and found information, and I am seeking the information that you know, and you are still pursuing more information, therefore you are still curious, but I'm curious in this context because you have already attained the information.
I do. This is one of my favorite dynamics. And of course, in explaining things to you, I learn things.
Absolutely.
And in hearing especially the metaphors that you do, which have been fantastic lately.
Okay, great.
I definitely learned some things. So, it's a give and take here.
Exactly.
Bestie, how close are you feeling to the universe this week?
I'm feeling close. Not too close, just like maybe an average amount of closeness to the universe. My hair is currently up in space buns, and that's really nice. I've seen a couple of really nice sunsets in the last couple of weeks, so that's been nice. I have been outside, but not in the way that I would like. I haven't had fun outside, and I would like to have some fun outside because I live in a place where it is temperate.
Sorry, rub it in.
Yeah, that's what the
it's
Plutonians...
been so cold here.
It's what the Plutonians and the Venusians are like. It's just so cold back here in Pluto. And it's just oh, I'm sorry, I'm on Venus, and it's just so warm. Whatever will I do?
Swimming in your lead pools. Yeah. Oh, it's okay. I'm not jealous at all. Nope.
It's fine. It's fine. How close are you feeling to the universe, bestie?
I have been admittedly introspective lately. Not even introspective, because I'm not looking inwards at anything interesting. I've just been in my own little shell because I've been in book editing mode.
Yeah.
So I have kind of tunnel vision on this one very specific aspect of the universe, but I'm not feeling the most connected to the universe that I've ever felt. I'll say that.
Yeah.
But we're still good. It's like when you just haven't talked to your friend in a month.
Exactly. I got to text the universe real soon, Yeah,
you got to keep that connection strong. But we're also keeping the connection strong here by making this podcast. And we're talking about a topic in space that you have been requesting for a while.
Because you keep teasing me with it, and I have no idea what it means. And so I'm just what could this possibly mean?
You want to tell them what we're talking about?
We're talking about hot Jupiters. And I think it might have been my first or second episode as co-host where I was I heard you say it. I was but I can't really think of what that means. It's I know I know Jupiter, and I knew Jupiter's giant and a gas giant. And so I'm maybe there's something with gas, but there's plural Jupiters. So hot Jupiters is a plural concept. So there are multiple Jupiters that are hot in some way, maybe because of the gaseousness, but I'm not really sure how that, I don't know. Yeah, so that's what I was wondering what that could mean.
Yeah, because I see your question is just,
Yeah. So now you understand why I'm I don't know what you mean by this, because there is one Jupiter, but maybe it's a but scientists are so literal, so it's are you being metaphorical, or is this there are multiple Jupiters, or is it planets like Jupiter, but that also feels metaphorical? So that's where I was I'm not sure.
Yeah. I mean, we're maybe not metaphorical, but we are comparative. We do love to put objects that we aren't super familiar with in terms of the objects that we are very familiar with. So
Definitely
when we
sense.
see a star that's around 6,000 degrees and is, yellowish in color, we say that is a sun-like star.
Right.
Astronomers, especially the planet people, are constantly looking for Earth-like planets. So we will compare other planets to Jupiter's, and we will point out the ways that they differ from our own solar system, Jupiter. So hot is in comparison to a cold Jupiter, which is what our Jupiter is.
Right.
And there are also warm Jupiters, which are kind of intermediate in distance. Yeah.
Okay. And then I assume we will find out why it's Jupiters and not Saturns or hot gas giants. So it's specific to the culture, the like, what would I say? The like atmospheric culture of Jupiter.
So there are two gas giants in our solar system, Jupiter and Saturn, and Jupiter's just the better known, more impressive one.
Okay.
So when we see other gas giants in other solar systems, we compare it to Jupiter.
Gotcha.
Although the size limit for hot Jupiters is typically between about a third the size of Jupiter and about 10 times the size of Jupiter. If you get something like 13 or 14 times the size of Jupiter, then that is actually, it tends to be big enough to be a little star. Or something close to a star, closer to a star than a planet anyway. Yeah, so there is a limit there. Saturn is about half the size of Jupiter, so it falls in that that range that I said. So if we saw Saturn in a different system much closer to its star, then we would probably call it a hot Jupiter.
Wow. So all Saturns are Jupiters, but not all Jupiters are Saturns. It doesn't quite work, but I was trying to make a...
It's okay, similar great. To how if we saw Venus in another star system, we would think that it's very similar to Earth. We would call it an Earth analog.
Would it be hot Earth?
Honestly, yeah, we probably would call it a hot Earth.
It's still
it is. Yep, you're so right.
Okay.
And we are a warm Earth.
Huh.
And Mars is like a cold Earth. Although if Mars had more of a magnetic field and was able to hold on to its atmosphere better and like more of a magnetic field and more gravity and was able to hold on to its atmosphere better, then it would be habitable-ish.
Right.
You know?
Right. So they keep trying to go there and see what they can do.
Yeah, because Elon Musk can give Mars a magnetic field.
Right, yeah.
But yeah, you're right. All Saturns, if we saw Saturn in any other system, we would probably compare it to Jupiter and not Saturn.
Wow.
Do you have any idea what makes a Jupiter hot versus cold or warm? Like, what is the biggest difference between them?
Yeah, I don't actually know, and I'm gonna guess something about its atmosphere.
Yeah, they all have similar like constructions to Jupiter.
So maybe it's closer to its home star.
Yes, exactly. The most important difference here is how close they are to their stars. So a hot Jupiter is much closer to its star than a warm or a cold Jupiter like ours.
Right.
I want to tell you a bit about Jupiter so
please
that you have that as the comparison point. So Jupiter in our solar system orbits about 500 million miles from the sun. That's a little bit more than 5 times the distance between Earth and the sun. It takes 12 years for Jupiter to do one orbit around the sun.
Sure. At that distance, I can imagine.
So at that point, it's traveling, 3 billion miles in 12 years? Yeah, 2 pi times 500 million? Yeah. So, but it rotates fairly quickly. The planet itself does one rotation every 10 hours.
Wow.
And it is 11 times wider than Earth. So you could fit approximately 1,000 Earths inside Jupiter.
And could we also fit it inside because it's gassy? Or are there still rocky elements that would prevent physical...
Rocky and otherwise. So the average temperature at the surface of Jupiter is negative 200 degrees Fahrenheit because it's so far away from the sun. It's not getting much energy. But as you get further inside Jupiter, the pressures get so extreme that temperatures also get pretty extreme and you get weird physics happening. So we think, and this gets into how these giant gassy planets are made, which I'm going to talk about more later. But we think that there is a rocky core inside and that rocky core might be, I don't know, about the size of Earth maybe, or Mars, and that it was large enough to gather through gravity all of this gaseous material, which is going to be mostly hydrogen because most of the gas in the universe is hydrogen, about 75%. when you move out from the core of Jupiter, you encounter weird layers. Like I know there's a layer of metallic liquid hydrogen where it's just like the temperature and pressure work out to squish hydrogen atoms into a structure where they act like a metal, like they can conduct things. So yeah, it's interesting inside Jupiter. And that is out, further in the solar system where it's not getting much energy from the sun. When you get Jupiters moving closer to their stars and getting a lot more radiation from their stars, things can get even more interesting. But that's Jupiter.
Okay.
So
yes.
Everything that I'm saying, you can compare to that.
This is a side note question. Can we bring something back? Like, can we bring that back from like a Jupiter to Earth? Like if we were able to like take a sample, have we done that? Can we do that?
We can't get into the metallic hydrogen layer.
Right.
Like
we can't recreate those temperatures on Earth, even in like a micro.
I think it's more about the pressures, maybe?
Okay. Gotcha. Okay.
Yeah, I mean, Jupiter is just such an extreme environment. Even if we could recreate those pressures, we can't also recreate the intense magnetic field that it has and the high wind speeds because it's rotating. This thing that is 10 times the size of Earth rotates completely in less than half the amount of time. Yeah, so it's rotating very quickly, and that makes its atmosphere quite turbulent and chaotic. That's why it has a big red spot, which is a giant storm.
Right.
It has weird lightning happening in the top layers of its atmosphere. These are extreme environments that are kind of unlike anything we can experience or create on Earth. And it gets even weirder when they are closer to their stars. So I want to tell you some stats about hot Jupiters to tell you how common they are. So they were first proposed in 1952 by Otto Struve. He was kind of an early user of radial velocities to study stars, looking at the wobbles of the star as they move towards and away from us and stretch the spectrum. We've talked about this before. Using radial velocities to study stars. And he imagined also, because this is back in 1952, way before we ever found an exoplanet, he imagined that if a planet were close to its star and massive enough that we would be able to see the gravitational influence of the planet in that radial velocity signal, which is exactly how we've found thousands of exoplanets these days. He wrote in his paper, quote, "It should be possible without much difficulty to discover planets of 10 times the mass of Jupiter by the Doppler effect."
He's like, y'all should have been found it. But like, I mean, here's a hint since y'all haven't gotten to it yet. Listen, if my brain was 20 years later, if my brain was 30 years later, like we would have been here. It's 1952 though. Like only so much I can do, but here's the answer so that you know, because
Exactly. Yeah, that's exactly what was going through his head. He actually wrote that first, and then he had to put it through like a professionalism translator.
Yeah.
Which was a person before the age of AI.
Yeah, just like backspacing on the... No, I think in some typewriters you can't even backspace.
No, he just had to write a different draft.
Dang.
Yeah.
Start over.
Yeah, I know.
Truly a zero draft.
So we did find them really quickly once we had the ability to find exoplanets. The first exoplanet we ever found around a main sequence type star, so a star that is actively fusing hydrogen into helium in its core, was a hot Jupiter. And I'm going to talk about that planet at the end. I have a section on famous or really interesting hot Jupiters that I want to talk about.
Famous hot Jupiters near you.
Yes. Paparazzi, get your cameras ready. They're walking down the red carpet. It's red because it's a blue carpet because it's so hot.
Jupiters, they're just like us.
I'm glad we make ourselves laugh.
We have fun here.
We do. So it was the first type of planet that we found around a fusing star, and they're one of the more common types of planets in our sample, not because they are inherently a more common type of planet, but because they are really easy to see compared to other types of planets. Hot Jupiters especially, they are close to their stars and they're big, so they're blocking out a large proportion of their star's light if they were to transit. So transit photometry, which is my favorite method for finding planets, works really well for hot Jupiters. But hot Jupiters are also really easy to find through radial velocities because they're massive and close to their stars, so they will make the stars wobble a lot. And hot Jupiters are even good for direct imaging. I mean, well, I guess the warm Jupiters, because they are big and warm, so they have kind of their own infrared signal. So if you can block out the light of the star, you can see the hot Jupiter right next to it. So it's just, in many ways, easier to find these hot and warm Jupiters.
Right.
So they are about 10% of the planets that we've discovered and confirmed. I'd say approximately 700 out of 6,000 exoplanets. And we think that they're around about 1% of sun-like stars. We expect that about 1% of stars that are around the mass and size and brightness of our sun to have a hot Jupiter. Hot Jupiters are typically found around sun-like stars. We don't expect them to be around low mass stars like the M dwarfs, the red type stars, because red stars are just so low mass and have so little material in their systems that they typically would struggle to create a planet of this size. Usually what you see around a low mass star is a bunch of close-in small planets like the TRAPPIST-1 system. Although, TRAPPIST-1 did a little extra and had 7 full planets for us to see. And then you don't necessarily expect to find hot Jupiters around high mass stars like the O and B type stars, because those stars don't really live long enough to form these planets in the first place.
Interesting.
Although if those types of stars were to form a planet, it probably would be one of these, like a gas giant. The Kepler mission, which was a transit-based mission, my favorite, we've talked about it before on the pod back when Corinne was here, it had 1/3 as many hot Jupiters in its sample as radial velocity surveys have in their samples. And we've tried to figure out why that is. Probably has to do with the fact that there are a lot of binary star systems in the Kepler sample, a lot of pairs of stars that orbit each other. And in those types of systems, which are really common, it's harder to have a hot Jupiter because the gravitational interactions between the two stars will kind of clear out a part of the disk where hot Jupiters need to get to.
So it's like it needs the correct conditions in order to both form and remain, because if the star isn't stable, it's not going to be able to grow into an actual hot Jupiter. It won't be able to grow to that like size and heat and pressure.
Yes, it does need the right conditions, but it also just needs enough time. And so it's less about the stability of the star and more about just how long the star is around.
Gotcha.
But that does lead me really nicely into the next section, which is how do hot Jupiters form? There are, broadly speaking, 2 different camps here.
Camps as in theories?
As in hypotheses.
Right. I was like, yes, in science. I mean, in general, but also, especially in science.
I mean, in like the colloquial vernacular, theory does mean something different, but, in this space.
Again, in a very special circumstance.
Right. So there's in situ formation, which means the hot Jupiter formed that close to the star. And then there are migration scenarios where the hot Jupiter formed further out in the disk and then migrated closer to the star over time. And there are a couple different mechanisms that can make that happen. So I want to start with first, like how do we think these giant planets form? And I alluded to it earlier with Jupiter's rocky core, but we think that probably these gas giants form through 2 different models. One of them is core accretion, where you get a rocky core that's large enough to use its gravity to pull other gas towards it and create a huge atmosphere. This is easier to do farther out in the disk where there's just like an abundance of gas. The other way that you can form these giant planets is through what we call gravitational instability, where if you have a disk of gas and other material, for some reason, maybe there's a type of wind or some weird magnetic field happening. For some reason, some of that material clumps together. And just because gravity works like capitalism and the haves continue to have more, other gas clumps onto it. So those are the two methods. Both of those methods for forming giant planets, it's going to be really difficult to do close into the star. So for a long time, we thought in situ formation probably wasn't realistic because these stars, they're giving off a lot of heat and energy, and that energy literally blows away particles from the really close regions around it, and you kind of need all of those particles to both create a core and an atmosphere, but also to gravitationally collapse on each other. They've estimated that core would need to be about 10 times the size of Earth.
Oh, wow. Of the hot Jupiters?
The core of the Jupiters, of the hot Jupiters, this is Jupiters in general, would need to be 10 Earth masses. Whoa. Sorry, not sizes, but 10 Earth masses.
Oh, okay.
So heavy, and because it's so heavy, it is very dense and it squishes in on itself.
Gotcha. Oh, okay. It squishes in on itself.
It's more dense than Earth, so it's 10 times as massive, but maybe only like twice or 3 times as big. So it's tight.
Yeah. Okay.
So we used to think that in situ formation probably wasn't very realistic, but more recently we've had models and seen some observations that say actually maybe sometimes it can happen. There was a paper I saw from 2023, and one of the authors I know through conferences, Dr. Melina Rice, is a co-author,
hey,
and they
Rice.
support in situ formation for some hot Jupiters. They have a paper called Evidence for Hidden Nearby Companions to Hot Jupiters, where they found that about 12% of hot Jupiters show signs of a, quote, quiescent dynamical history. Do those words mean anything to you?
Nothing scientific and everything that is straight out of the gossip. Like, this sounds like a conscious uncoupling. It's the hot Jupiters have secret side flings. About 12% of them have a quiescent dynamical history. It sounds like you're trying to be like, Jupiter is poly, and we don't want to use that language. Like, what are we...
I mean, do you see how many moons Jupiter has? Of course Jupiter is poly.
I mean, we've known this since the ancient times, actually.
You're right. Jupiter has never been monogamous. Like, maybe on paper, but no, never truly, for one woman only. So a quiescent dynamical history means that it hasn't moved around much.
It means the opposite.
Yes.
Yes,
exactly.
It's like, oh, they actually don't be outside, Like,
it's actually, no, because you cannot move around much and still have lots of pieces.
True.
No, like the pieces just come to you.
True. They do come to you because gravity.
You're learning, bestie.
See, if you just translate it.
I'm sorry.
No, that was great. See, if you translate it into whatever this is, I will start to understand.
Amazing. Yes. So when you hear quiescent dynamical history, that means that it hasn't moved around, so it got to keep all of its companions.
Mm-hmm.
Yes.
Interesting.
And these companions aren't necessarily moons, but other planets in their systems that are in close orbit around it, or just seem to have stable positions in their stellar systems. Whereas if the giant planet had moved in and around them, then we would expect there to not be stable planets that are that close to the star.
Right, because it would have disturbed everything moving in. Giant gaseous planet just kind of coming into your flow, of the neighborhood, messing everything up, just making things unstable. We don't want that.
No. Well, we might sometime.
We might.
Yeah.
But some planets might not want that,
Well, sometimes it actually is for the good of the neighborhood to have the giant planet come in and sweep some things out. But we'll talk about that because that's kind of what happened in our solar system. Yeah.
Ah, okay.
Mm-hmm. But first, I need to talk about the migration hypotheses.
Yes.
Hey friends, it's me. Connie is messing with the office thermostat. We have a special stellar fusion setting that cranks up the temperature really high, but then instantly fuses our sweat molecules into platinum dust. So it's pretty nice. We like to collect that and then use it to raise funds for things around campus. But while that's happening, I am going to share some messages with you. The first message is a thank you, a huge thank you to all of the patrons who support the show every month. We are an independent podcast, so it would be really hard to make the show without your support, and I appreciate it so much. I also want to give a special shout out and another huge thank you to my Sun-like stars, Scott Reynolds, Tom T, Nicole Bartlett, Ashley Shambo, Mark Mahoney, and Bruce Sedloff. Thank you, my golden friends. And your mass is perfect, so thank you for holding down the entire Pale Blue Pod solar system with your gravitational influence. If you would like to join this awesome group of people, you can do that on Patreon. You would be supporting an indie podcast. You could hear your name on the show, make it onto the patron star chart, and get research notes for most episodes, all for $5 a month at patreon.com/palebluepod. You can also make a one-time donation as a supernova at the PayPal link in the episode description if a monthly thing isn't for you. And of course, if you can't support the show financially right now, I understand. We still love you because you are space. The best way to help Pale Blue Pod grow is actually to get more people listening to it. So if you could take a link to this episode and send it to someone who you think would really enjoy it, get more people listening to Pale Blue Pod, more people befriending the universe, then we all win in that scenario. And I would like to say thank you in advance. My next message is a podcast recommendation. It's another show in the Multitude Collective called Wow If True. Wow If True is your one-stop internet culture shop explaining how what's happening online shapes the real world. And the hosts are the internet experts and real-life besties to unravel it all. One is tech culture journalist Amanda Silberling, and the other is science fiction author / attorney Isabel J. Kim Esquire. Most importantly, they are the only podcast that will mention Neopets and horizontal mergers in the same episode. They're asking and answering your burning questions about the internet, like, are the AI overlords coming to take our jobs? And if so, why are the AIs so awful at playing Pokemon? They also just did an episode about AI pets. Amanda has been using an AI pet called a Mouflin for a while. I saw it on TikTok and was creeped out, but I like this episode because it tells me more about this thing. So why don't you check it out and form your own opinion about AI pets? You can do that by checking out Wow If True wherever on the internet you find your podcasts. New episodes come out every other Wednesday. Okay, in the time that I've been talking, Connie and I have sweated out enough platinum dust to pay the entire incoming class's tuition. So let's get a drink of water and then continue this conversation about hot Jupiters. So one of the migration hypotheses is that there are torque forces, so rotational forces that act on the planet from the gas disk around it. Yes, gas can actually be that powerful. It can move Jupiters, especially early on in a system's history where there's just a lot of gas and it has a lot of energy from that collapsing cloud of gas that formed the star. And so this torque migration will over time just like steal energy from the gas giant's orbit, or maybe like give it some energy and then it slings back in. But over time, this exchange moves the planet closer to the star. If it migrates too close, which is very possible, then it will get absorbed by the star.
Right.
And we've seen what might be evidence of that. We see stars that, have nova bursts where they don't go supernova, but they get temporarily brighter. And that could mean that it absorbed some extra material. So they might get ripped up by the star. But if they have enough of a magnetic field, and if they happen to fall into like the right distance from the star, then that magnetic field can save them. And we do expect that to scatter planets. And we have seen a lot of hot Jupiter systems where there's the hot Jupiter close to the star, and then maybe there are planets further out, but like nothing around that hot Jupiter's orbit.
Do other planet types migrate this way?
Like ice giants or something?
Yeah.
Ice giants, if they migrated closer to the star, they would melt and would probably become some type of gas giant or a terrestrial planet eventually. Maybe a Neptune. Yeah, if a Neptune moved in, you know.
But I also just mean like the migration in general. Like, just is this how planets can move in general, or is it specific to the gassiness of the giants?
It is specific to the mass of the giants. The fact that it is so massive actually means that it has these stronger interactions through gravity with material around it than a smaller, less massive planet. I want to quickly run through the other migration scenario. And this is a scenario where the giant planet has some sort of gravitational interaction that's stronger than the torque force from the gas in the disk. Like maybe it interacts with another planet, or a star comes by and knocks it off or something. And it gets put on a really eccentric orbit. So sometimes it's really far away from the star, and sometimes it's really close to the star. Every time it comes closer to the star, it will have some sort of interaction, especially through like tidal gravitational forces that mess with the rotation of the gas giant. Over time, the planet will just cycle closer and closer to the star until it is a hot Jupiter. And we've seen this kind of in action, like in an intermediate step, and that might be what like warm Jupiters are, like as they are like actively getting closer to their stars.
Right.
And we also would expect that these high eccentricity planets, because they got their high eccentricity through a collision or interaction of some sort, that they aren't aligned with the plane of the system, so they might be knocked off at an angle, and that is often what we see with some of these like intermediate phase hot Jupiters that form through the eccentricity migration. I think it's actually called tidal migration.
Is it that if its trajectory is showing that it can get closer, it might become a hot Jupiter, but it may not become one?
Yeah. There's a lot of, well, it might be this or it might be that, or it's probably in between these two things, and who knows, types of answers in astronomy.
Yeah.
Our Jupiter has migrated.
Oh.
Yes. In our own system, we have compared models of solar system formation to what we observe. And it seems likely that in the past, Jupiter actually, so right now it's about 5 times the Earth-Sun distance. It probably, according to these models, started at 3.5 times the Earth-Sun distance, and then migrated inward to about 1.5, which is around where Mars is, and then outward again to about 5. And that hypothesis is called the Grand Tack hypothesis. It was proposed in 2011, and the lead author of the paper is named Kevin Walsh. I have a quote here. They called it the Grand Tack hypothesis because, and I quote, "This change in direction," when it goes in and out, "this change in direction is like the course that a sailboat takes when it tacks around a buoy."
He didn't even get the word grand in there, but like, okay, I guess.
Well, it's, you know, it's the grand hypothesis that where the Jupiter made this tack shape. I'm just saying, like, is that not... I've never met this man. I'm going to say something nice about him before I looked up his picture, and he is a lot more attractive than I expected him to be. I'm just saying, he does kind of look like an off-brand Austin Butler from his early faculty photos. I will say that. Yeah.
Okay, go ahead.
But is that not the, like, waspiest, like whitest way to name this hypothesis for Jupiter's migration?
You
like,
know, when you have a sailboat,
to a sailboat?
You know when you have a sailboat and it just goes in and out of the buoys, it's like that. Just like that. Nothing else. Just like that. Everyone's going to understand this one. I don't know why he's like weirdly British.
Right.
But
That's the thing.
okay.
That's the thing. Everyone's gonna understand this one. That's the part that gets me. Like, no, bro.
No,
But
this is very specific to you and your Harvard or Yale or somebody, homeboys.
Yes. But we do now have this hypothesis, and it's been, tested a few times, and we still think that this is what happened. And I found a paper from 2024 in the research notes for patrons, if you want to join our Patreon, that says that likely happened, that migration likely happened in the first 100 million years after the sun formed. And it would have to have happened early on because we see close planets to the sun. So we know that this Jupiter migration happened before the terrestrial inner planets had the chance to form, which also tells us that these giant planets formed earlier. So there are like all sorts of clues about planet formation in this hypothesis. So these hot Jupiters, I've said they're about typically 1/3 to 10 times the mass of Jupiter. They are low density. These gas giants are actually some of the lowest density planets because they're just puffy gas atmospheres.
Right.
If you had a pool of water big enough to fit Saturn would float.
I think I have heard this before, and it sounds nice.
Okay, good. So these hot Jupiters, they're low density, but they are still huge and massive, and they are so close to their stars that they orbit in less than 10 days.
Wow.
For the record, it takes Mercury almost 90 days to orbit the sun.
And they're still spinning real fast, like Jupiter?
Most of them are tidally locked to their stars. So they rotate in the same amount of time as they orbit. But, about 3 days is typical for an orbital period. So yeah, they are spinning every 3 days. But tidally locked planets have completely different climate models than the types of Jupiters that are orbiting far away from their stars, because there's this one point of the planet that is always being blasted by heat and energy from the sun right above it. And then on the other side, it never sees any of that energy. So there are these interesting transport mechanisms, and that puts a lot of storms in their atmospheres. And it's just complicated and messy and interesting.
Right.
Yes. Very cool. Very cool physics going on there. The average day side temperature, so the day side is the side that's facing the star. The average surface temperature there is about 3,000 degrees Fahrenheit for most hot Jupiters. But there are also ultra hot Jupiters.
I mean, of course there are.
Of course there are. That get up to, I think I saw something like 8,000 degrees. And that is basically as hot as a low temperature star. So the line between Jupiters and stars, we are actively trying to study that threshold.
Right.
And see where the line falls. Their atmospheres are thick and opaque. You find lots of hydrogen, probably lots of carbons and sulfurs and nitrogens maybe in there. But the fact that the atmosphere is so thick and opaque makes it hard to cool down, actually, because it's kind of like when there's a really cloudy late afternoon here on Earth, and you get after a hot day, and then you have a really warm night because the clouds trap in the heat. The clouds here are trapping in the heat that it gets from the star.
Yeah, because there's never any cool times.
Exactly. Yeah. It can be difficult to tell the difference between these ultra hot Jupiters and little stars, but they have different temperature profiles because in a star, the heat is coming from the inside, and in these hot Jupiters, the heat is coming from the outside, and we can kind of track that.
Right.
Oh, a fun thing about hot Jupiters is that they have high rates of what we call atmospheric escape. So they are so close to their stars that the heat and energy will kind of excite particles in their upper atmospheres so much that they vibrate away from the hot Jupiter. It's like they're shimmying away from all the heat.
Shimmy, shimmy,
and
shimmy.
so they can lose up to about 1% of their total mass. I couldn't find if that was per year or overall, but it is more extreme early on in the planets and the star's life, because stars start off really magnetically active and like energetic, and then they kind of chill out, or calm down, I should say, calm down over time. And so the planet doesn't get blasted by that much. And so it has lower rates of atmospheric escape later, but they lose a big chunk of their mass.
Yeah.
Whereas Earth actually gains mass over time. We do experience some atmospheric escape at the top of our atmosphere, but we also get a lot of cosmic dust that falls on us every year.
Oh.
So Earth is gaining weight. Good
for her. Yeah.
Yeah, good for her. Good for Gaia. Yeah, I wrote in my notes, I think it was mostly just because I liked this term. You find in these hot Jupiters that a process called ohmic dissipation is reduced. Ohmic dissipation is the fancy way of very nice, very nice. It's the fancy way of saying heating through resistance. So, and the ohm is the unit for electrical resistance.
Gotcha.
So ohmic dissipation gets kind of broken down in these hot Jupiter planets that have temperatures above about 2400 degrees Fahrenheit. And it's because their magnetic fields are so strong that it actually disrupts the motion of the charged particles, the ionized gas in the planet's atmosphere, so they can't move in the way that would actually create heating through resistance.
Right.
So there are just weird things happening inside these hot Jupiters. And I do have a picture.
I see.
I just wanted you to see. So I have here a diagram of the magnetic field activity around a hot Jupiter type planet. So you can see the day side on the left and the night side on the right. And then there are all these curved lines around it, which tells you where the magnetic field activity goes.
Huh.
It comes out in these loops from the poles that go like out from one pole and around and then down to the other in these giant circles.
What does that mean for the poles, which don't have those lines? Like that's still, it's just illustrative.
Yeah, there are actually going to be a lot of magnetic field lines close to the poles.
Right.
Because that's where they all gather.
Whoa. What happens there? Is that it?
Jupiter has a aurora. You know, there are electric storms that happen when you get high concentrations of these charged particles.
Right. Cool.
Yeah. We study hot Jupiters through, several different telescopes. Some of the most successful hot Jupiter missions have been WASP. This was the wide-angle search for planets. It was a ground-based transit survey, so they were looking for the shadows that the planets cast on their stars. It was a lower-resolution survey, and it had to deal with looking through our atmosphere, which creates a lot of blurriness.
Right.
And so it was much easier to find bigger planets, so WASP ended up finding a lot of hot Jupiters. There was another survey called HATNet. It was the Hungarian-made automated telescope network exoplanet survey.
Wait, so
exoplanet survey was just separate. It was the HATNet exoplanet survey.
Okay.
Yeah.
I was like hatneties.
This was a system of 7 different ground-based telescopes. It's not an interferometer because they all weren't working like together at the same time, but they would just pool their data together. And again, because it's a ground-based system, it's going to be easier for it to see large, massive planets. Since they started operating in 2003, they've discovered 70 exoplanets to date. That's a quote from their website, but I also saw that their website was copyrighted from 2018. So I don't know if they found anything since.
Right.
And then a hot new survey that is finding a lot. Hot new survey enters the villa.
Exactly, yeah.
Ian Sterling, when will you start narrating scientific research?
Honestly, it would make it so much more interesting.
Honestly, yes. So the hot new survey, yes, I stand by my words, is called TESS, the TESS Grand Unified Hot Jupiter Survey. And TESS is the Transiting Exoplanet Survey Satellite. So it's the Transiting Exoplanet Survey Satellite Grand Unified Hot Jupiter Survey. Rolls off the tongue.
So easily. I don't even remember half the words you said. And I'm looking at them on the agenda.
I know. So this survey started in 2022 and is ongoing. Their goal is to comb through TESS data. TESS is also looking at the shadows cast on stars by their planets, and it has a huge back catalog of data, and they are combing through it to find hot Jupiters that have been missed because they were, I think, mostly focused on smaller, maybe more Earth-like planets. And they've found over 50 hot Jupiters so far.
Nice.
And expect to find more. I know one of the people who's involved is Jessie Christensen, and she was, if not like the person who started it, she was heavily involved in starting the NASA Exoplanet Archive. So she knows a thing or two about cataloging exoplanets.
Yeah.
And then these atmospheres around hot Jupiters are so large that we can study them. So we have, and we typically will study them with a space-based telescope like Spitzer, which is in the infrared, Hubble, which is in the optical and infrared, and the JWST, which is also, it's like a successor to Hubble, so also in the optical and infrared.
Gotcha.
I do have some famous hot Jupiters.
Please tell me about the famous hot Jupiters.
Okay, and we can kind of breeze through this. I think the most famous hot Jupiter is 51 Pegasi b. This was the first exoplanet discovered around a main sequence star in 1995, y'all.
Wow.
A great year. A great year. You know, great vintage.
Indeed. Some great things
the
were
crop
made.
from 1995.
Just, just like truly exquisite, smart, intelligent, cool.
Yes. Clueless came out in 1995.
January of that year seems like it would be an important time. I can't really sense why. Like, I was just 5 years old, but like something else must have happened that was kind of cool, I guess. I got to think about it, though.
Yes.
I have a couple months to figure it out.
Yeah, you do. But I do like to say that I have never lived in a world that didn't know about exoplanets.
Yes, that explains so much.
So this first exoplanet ever discovered, well, actually, there was an exoplanet discovered around a pulsar, but because pulsars are the kind of last dying breaths of stars, they're like the last stage of a star's life, for some reason, that didn't count. For some reason, they were like, no, that doesn't prove that there are other planets around other stars. So that happened in 1992, and then they waited another 3 years until they found a planet around a main sequence star, and then they got the Nobel Prize in physics.
Come on, man. You could at least like slide, the people before you some. Like, if you find something from somebody else, like, give them, like they deserve. Like, come on, man. It's like, no, but this one's a big deal. No, but this was a big deal.
Yeah.
That way doesn't count. Yeah. So it didn't count like before they won. Like, no one cared. Is that what you're like? What is it that made this one kind of pop off, I guess?
Right. The difference was that the first planet was around a pulsar, which is not a main sequence type star. And the planet found in 1995 was around a main sequence type star. And the whole question that the exoplanet community was trying to answer in the first place was, are there planets around stars?
Okay.
I guess maybe even more specifically, like, can we find Earth-like planets around sun-like stars? But because pulsars don't fuse in their cores, then it didn't count. I know. It's such a technicality.
Yeah, they should get a certificate or something.
Yeah. So the planet, the 51 Pegasi b, was found around a sun-like star called 51 Pegasi, and it's about half a Jupiter mass, but 1.25 Jupiter radii, so it's puffy. It's big. They tend to be even less dense than regular Jupiters because as they get more energy from the star, it will puff up the gaseous atmosphere. It had a 4-day orbit, so it was really close to its star. And this planet, I know, is the most famous hot Jupiter because it has a whole postdoctoral fellowship named after it. It's privately funded, so it's not in danger from current shenanigans,
right?
Which is good.
Yeah.
Thank you to the Heising-Simons Foundation. And it provides up to $450,000 of funding for 3 years.
Nice.
With the option to extend. So yeah, I know it's the most famous.
Yeah.
But another one that I think is probably, it's not famous, but it's notable. This is TOI-2109b. TOI stands for, I'm pretty sure, TESS Object of Interest. So it was found with the TESS mission.
What did
We also used to have KOIs, or Kepler Objects of Interest, for the Kepler mission. This is just like how we label the planets in the catalog.
Right. Okay.
So TOI, it was discovered with TESS in 2021. It is 1.8% the distance to its star as Earth is to its sun.
Whoa, they kissing.
Yes.
That's close.
Yes, bestie. I said the average period for a hot Jupiter is 3 days. This one orbits its star every 16 hours.
Wow.
It is 5 times the mass of Jupiter, so it's a big boy, but only 1.4 times the radius. Now I'm wondering if I missed a decimal. No, 5.2. I was not careless. I did not forget a decimal. It truly is 5 Jupiter masses and 1.4 Jupiter radii, so it's denser than Jupiter.
Huh.
I mean, I guess it would have to be to survive being that close to its star without being ripped apart, because that is another thing that happens to these Jupiters. The tidal forces will, stretch
just
them.
Like face to face, just like nose to nose, just like, I dare you. I dare you. I dare you to rip me up. I dare you to rip me up.
This planet is saying to its star, not touching, can't get that.
I'm not touching you.
Can't get
I'm
that.
not touching you.
So that's maybe that's the brattiest hot Jupiter out there.
Because that sounds crazy. I got to look that one up.
And then we have, I guess, the nicest hot Jupiter, because WASP 47b showed us that hot Jupiters can play nice with other planets. It is pretty similar to Jupiter's density, about 1.17 Jupiter masses, but 1.14 Jupiter radii. So, that's within a margin of error. It was found using the transit method, so it passed in front of its star and cast a shadow. And its period, it's just leisurely strolling around its star, taking 4 days to do an orbit.
Hello, darling. I'll see you on the other side round. No, because they're always facing, right? So it's like, yes, I see you, darling. Oh, wait. So the other one, TOI 2109b. So it's facing its star tidally locked. Yeah. So it's literally just like following it. So does that mean that the star rotates every 16 hours as well?
I don't know the rotation period for the star, but I doubt they have linked up, because the gravitational influence of the planet on the star is going to be fairly weak. So I don't think that they match.
Oh.
I think our sun rotates every 10 days. This is future Moiya coming in with some fact checking. The rotation period of the sun at the equator of the sun is about 25 days, but the sun doesn't rotate as a rigid structure, so the equator moves faster than the poles. The material at the poles will rotate roughly every 35 days, if not more, and that varies over time because, again, the sun is not a solid piece of singular stuff. It's fluid, and it moves separately, which is cool. So, and this is a sun-like star-ish. So, so all 3 of these planets orbit within 1 astronomical unit, 1 Earth-Sun distance of its star, and the other 2 planets are both mini Neptunes. So they're bigger than Earth. They are probably gas giants themselves, but small. But these all have high uncertainties, so we're not totally sure if that's what the system is really doing. But still, it is a good candidate for in situ formation because it would be really hard for this Jupiter to hold on to its companions if it had migrated in.
Right.
And then the final hot Jupiter I want to talk about is WASP 39b. This is a hot Jupiter that might have an exomoon. We have never actually found an exomoon, although there have been some candidates, but we haven't confirmed one for sure, because it's hard enough to find planets. Moons are even smaller and darker and cooler, so it's hard to see them.
Right.
But the planet itself has a 4-day period. It's a third the mass of Jupiter, but 1.3 times the size. So it's low density. It was discovered in 2011. And in 2023, there was a paper that announced they'd found sulfur dioxide in its atmosphere, probably with Hubble or JWST data. And then I found a new paper from October of this year, October 2025, that claimed that sulfur dioxide, it's not actually coming from inside the planet. It's coming from a moon orbiting the planet and depositing that sulfur dioxide on it. They compared the moon to Io in our own solar system, which is the most volcanically active body in the entire solar system. And we do see Io outgassing this material that falls onto other moons and Jupiter and creates this kind of like cloud of gas that you can see. And so they think that's what they're seeing in WASP 39b, that it's actually a moon outgassing this sulfur dioxide, creating a ring of material that we're seeing and assuming is coming from inside the planet.
Right. Wow. The moon is just sprinkling little bits of itself like, hi, I'm here too. Thank you. Thank you.
Don't forget about me.
Don't forget about me. Thanks.
Yeah. As hot Jupiters, they don't want to be forgotten.
Honestly, they're trying to find a way to not just be compared to Jupiter. I guess she's all right, but we're bigger. We can be denser, and we have our own thing going on, okay? We're migrating, or maybe we're just, staying in the same place, being iconic.
Yeah, for maybe about 12% of us.
Yeah.
So did that answer all your questions about hot Jupiter?
All of my questions and more. I learned so much, and I retained many things about how planets work as well. Good. Yay.
Okay. On that note, I know none of you are probably Jupiters, but you are all hot. And I know that because you are space.
Pale Blue Pod is hosted by Dr. Moiya McTier and Connie Gibbs. Moiya created the show with the funny and talented Karine Caputo with help from the Multitude Productions team.
Our theme music is by Evan Johnston, our cover art by Shay McMullen, and our audio editing is handled by the superlative Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Instagram or check out our website, palebluepod.com.
I, Moiya, am Go Astro Mo on all socials.
And I'm @ConStar24 on Instagram.
If you want to support our show, join our community at patreon.com/palebluepod or send this episode to your family and friends group chats.
We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
Thanks for listening to Pale Blue Pod. We'll be back next week.